All right, everybody, here we go with part 3 of our data analysis lecture. We ended up, right, talking about probability level, the p-value. And p-value is the probability that any differences between groups are due simply to chance. So remember that in communication disorders, we're going to set that at 0.05. which means that the probability that the differences happen by chance is 5% or less. So that p-value says what are the chances that any differences are just random differences and not true real differences because of the independent variable. So p-values at or below 0.05 are said to be statistically significant, meaning that there's only a 5% chance or less that the outcome would occur if the null hypothesis is true. All right, so there's less than a 5% chance that any differences are random, and if differences are random, that means the null hypothesis is right, that things are the same, but a low p-value tells us things are probably not the same. So that ends up giving us 4 possible outcomes, right? Choice 1, the researcher concludes that the null hypothesis is true and is correct. All right, so you get a p-value of 0.23, which tells us there's about a 23% chance that any differences are just random, right? So that's too much to be able to say there is a difference. So we have to conclude that the null hypothesis is correct. There are no differences between groups. And then let's say you were able to climb up a mountain and find the old wise man, and he gives you one question about life that he will answer. And you say, actually, all I really want to know is, was my research paper correct? Was the null hypothesis true? And he says yes, there really were no differences between groups. And you go, phew, okay, I'm a good researcher. I made the right decision. There are no differences between groups. Choice 2, the researcher concludes that the null hypothesis is false and you're correct. So you get a p-value of 0.01, which shows that there's a 99% chance that there are differences between groups, that the null hypothesis is false, that therapy A really is better than therapy B. You have a party, you get your paper published because you showed a difference. You climb up that mountain and the old wise man says, yes, you were correct. Therapy A, if you give it to everybody in the world, therapy A would be more helpful than therapy B. Great job. You're a great researcher. Okay. Choice, however, there are 2 more choices, unfortunately. And these are type 1 and type 2 errors. So the type 1 error is choice 3. The researcher concludes the null hypothesis is false, but it's actually true. And this is a type 1 error. So you get a p-value of 0.03, which means there's only a 3% chance the null hypothesis is correct. However, or not however, right? So you say, wow, there's a 97% chance that the research hypothesis is true. There is a difference between groups. Therapy A really is better than therapy B. You throw a party. You get your paper published. And then you climb up that mountain and the old wise man says, yeah, sorry, actually, if you give it to everybody, therapy A actually is no better than therapy B. There was only a 3% chance of that happening, but 3% chances happen all the time, right? It's almost impossible to win the lottery, but somebody in the country is going to win the lottery tomorrow, right? So, 3% chances just mean that there's a 3% chance that something will happen. So sometimes we're going to say, well, there's only a 3% chance that things are the same. I'm going to conclude, therefore, that they're different. But in reality, this time you're wrong. There's no difference between groups. And then type 2 error, the other error, is choice 4, where you accept the null hypothesis, you get a p-value of 0.12, meaning there's only a 12% chance that the null hypothesis is true, that there really is no difference. There's an 88% chance that there is a difference between groups, but that's not good enough, right? We need to have a 95% chance that we're right, that there is a difference before we can say there's a difference. So you get a p-value of 0.12. You climb up that mountain and the researcher says, yeah, you totally, or not the researcher, the old wise man says, yeah, you totally messed that up. You didn't have enough people in your study. There really is a difference between groups. Therapy A is better than therapy B. You just messed up your research. So there are 4 ways to go. With a type 1 error, the researcher says, aha, there's a difference. I'm great. I'm going to publish my study, but she's actually wrong. There is no difference between groups. Choice 4, the researcher says, oh, shoot, I didn't find a difference, but in reality, there is a difference between groups. All right, so those are type 1 and type 2 errors. All right, so the process, step 1, we're going to review the null hypothesis, right, which will almost always be there is no difference between groups. We're going to decide on a probability level. We'll agree to set ours at 0.05, because in most areas we're going to set it at 0.05. Sometimes in drug studies and things like that, they might set it down at 0.01 so that they're 99% sure there's a difference, but we're going to set ours at 0.05. We're going to select the appropriate statistical test, which we'll talk about in a second here, for the type of data and number and type of variables that we have. And it could be either a parametric or a non-parametric test. So these are going to be inferential tests, and they test the probability that the findings were due to a sampling error rather than a true experimental difference, right? So how do we know if 2 groups are different just because of random chance and sampling error, or if two groups are truly different because of our independent variable, our therapy, our drug, or whatever? So we've got 2 types of tests. We've got parametric tests and we've got non-parametric tests. To do a parametric test, data should be interval or ratio. So those are the last 2 kinds that we talked about. Remember, interval data is like a test score. You get scores from 0 to 100. Ratio data is true, what we would call true numbers, right? So this is going to be data that we can multiply, we can divide, we're going to think of as real numbers. The data should be normally distributed, so like everybody in group A can't get a 15 and everybody in group B can't get a 35, right? There's got to be some distribution between the scores. You've got to have at least 8 people per group in order to get a reasonable answer. And you've got to have similar group variances. So, one group, can't be, all the scores can't be between 15 and 17, and in group 2, the scores range from 0 to 1,000, right? So you've got to have a sort of similar group variability and variances. All right, so the most common parametric test is a Ttest. This is used to compare 2 group means. So think of your data as if, one of the reasons it's called a Ttest is if you have your data, you would draw a T on the paper. At the top of the left side, you write group A. The top of the right side, you write group B. And then your data goes down the pages on both sides. And the T really is the difference between the group means. So what's the average in group A? Minus what's the average in group B divided by our error. And by error, we really mean our standard deviation. So how much do scores differ from the mean? So we're going to take a look at this quickly. So let's say this is our data, right, for group A and group B on the post-test here, right? So I'm going to copy group A's data, edit, copy. I'm going to go to our class page here, if it will let me. I'm going to go to our Ttest calculator. We're going to go to group 1. I'm going to pop those in. No, I don't want any of that. Thank you. Edit, paste. Whoops. Edit, paste. Okay. Then we're going to go to group 2. Let me go back to where we were here. Let's go here. All right, ready? Edit, copy that group. We're going to go back to, where did our Ttest calculator go? Okay, right here. We're going to go edit, paste. Okay, so here's our data. We're going to calculate. Let's see what we get here. All right, so let's see if I can make this any bigger. All right, so the average score in group 1 was 62. Average score in group 2 was 72. It gives us the standard deviation was exactly the same in both groups. We had 8 people, the N, 8 people in each group. So let's go here. So we got a p-value of less than 0.0001, right? So by conventional criteria, this difference is considered to be extremely statistical significant. So we have significant differences now between our two groups, right? So that was, we can say, yay, we have significant differences. Okay. Now let's go to our next group. So now, so that's group A, group B. Now I'm just going to change group A's data here. So we're going to copy that. We're going to copy that, and let's see what we get here when we do that. So let me take this and go edit, paste. So we put different data in group A, keep group B the same. We're going to calculate now. All right, now we're a little closer, I think, in difference. So we've got a mean of 62 in group 1. We've got a mean of 72 in group 2. Standard deviation is much higher in one than the other, and it comes back, we get a p-value of 0.16 basically. So this difference is not statistically significant, right? Because our p-value was above 0.05, so it's going to say nope, not different. We have to take the null hypothesis then is correct. There's no difference between groups. Any difference was just random chance, it's going to tell us. All right, so that data was not different enough to do that. All right, so that's really quickly what that t-test is going to tell us. All right. So factors that are going to give us a t-score, right? So we get a t-score, and from that t-score we find what we need. So the difference between the means, right? So the group differences are going to be a big part. Amount of the variability is going to be a big part. So, right, how much variability was there within each of the groups? And then also the sample size is going to be important. If we get 1,000 people in our study, the test is going to be a lot more confident to say, yeah, there probably is a real difference because you got lots of people in it. Whereas if you got the same average scores, but you only had a few people in your study, your test is going to say, you got a good difference, but there aren't enough people in your study for me to know if there's really a difference. We're going to say there's no difference. We'll give a higher t-score and therefore or a lower t-score, but a higher p-value. And there'll be no difference between the groups. You can have, and there are different kinds of t-tests. There could be an independent or unpaired t-test is used for a between group study. So if I'm comparing people, group A, group B, how did they do on the post-test? That's going to be an independent or unpaired study. But you can also have a dependent or a paired t-test where, let's say you have one group of participants and they go through a study, you give them a pre-test, you give them a post-test, and you're comparing the the same people taking the pretest versus the scores of the same people taking the post-test, that would be a within-group study. So you'd use you'd have a dependent or a paired t-test for that. Okay, and we'll talk a little bit more about that in a little bit, or maybe in a different lecture. An ANOVA. ANOVA is an analysis of variance, and the ANOVA is almost the exact same thing. The only difference is you'd use it for more than two groups. So if you've got two groups, you're going to use a t-test. If you have more than two groups, you'll use an ANOVA. For a t-test, you get a t-score. For an ANOVA, you get an f-score. And an f-score is the variability between the groups divided by the variability within the groups. So same thing as a t-test, just with more groups. You can do a one-factor ANOVA, which is going to be between groups. And that compares the means of more than two different groups with one independent variable. You can also have the same thing with a within-group ANOVA, also referred to as a repeated measures ANOVA, because you're repeating the test with the same participants in a within-group study. But you can also have, with an ANOVA, you can have as many different independent variables as you want. So you can be looking at, all right, how did people do on the test? How did they do based on gender, based on severity level, right? This could be two factors that you're looking at, two independent variables on a dependent variable. And so, we can just kind of go on and on with different factors, different levels within an ANOVA, which is kind of neat. So we've got the t-test, we've got the ANOVA. The last kind of parametric test we're going to talk about is a correlation. And a correlation, we would get an R statistic. So in a t-test, we get a t value. In ANOVA, we get an f value. And in a correlation, we get an R value or an R statistic. And a correlation is a relationship between the two variables. Remember that in correlations, we don't get cause and effect, right? In the t-test and in the ANOVA, we're going to usually try to say, yes, the independent variable caused a change in group A. But in a correlation, we're just looking at, do things go together? Are things related or not? So here we're looking at a relationship between two variables, and there are three ways that we can look at correlations. We can look at the direction of the relationship, at the strength of the relationship, and at the significance of the relationship. Okay, so for the direction of the relationship, we can have positive or negative, right? So positive, two variables are related in that when one increases or decreases, the other does the same. So one of the best examples in our field is mean length of utterance and age. When a child is 1, they should have an MLU of at least 1. When a child is 2 years of age, their MLU should be 2 or a little higher. When they're 3 years of age, their MLU should be 3 or a little higher. When they're 4, it should be 4, right? So as age goes up, MLU goes up. They're definitely related to each other. Right. Now, there can also be a negative relationship, and here we can look at age and number of ear infections per year. Most ear infections are going to be in the first and second year for children, and they're going to drop off. So they'll have the most ear infections before their first birthday, then before their second birthday, they'll have fewer again before they're 3, they'll have fewer again before they're 4. So as their age goes up, their ear infections on average go down. So that's a negative relationship where when one goes up, the other goes down. All right, then we've got strength of relationship. So how close the data points are to the line of best fit. So again, we're looking at an R, and that Pearson R can be anywhere between -1 to a +1. And what's important to remember with strength of relationship is that the farther away from 0, the stronger it is. So anything, so plus or minus 0.25 to 0.49 is a weak correlation. 0.5 to 0.74 is a moderate correlation, and 0.75 to 1 is a very strong correlation. So, and again, it doesn't matter which way. So if you get a correlation of negative 0.95, that is a really strong negative correlation. If you get an R value of plus 0.84, that is a strong positive correlation. So you can have strong positive, strong negative, weak positive, weak negative. So strength of relationship tells us how strong that relationship is. Finally, you can get significance. So you can get a p-value for the correlation. However, the strength is going to tell you more, because if you have a lot of people in your study, you might get a p-value of 0.04, which would tell you that there is a significant relationship, right? It's 0.05 or lower for that p-value, but yet it's a really weak correlation. So it might be like 0.25, or it might even be lower than that. But if you have enough people, the test will say, yeah, there is a correlation. So you get a good p-value of less than 0.05, but it's a really weak, unimportant correlation. So the most important way to look at the strength and importance of a correlation is by that R value, not by the p-value. But you can do the p-value, and you can do both. You can get an R value and a p-value if you want to. All right, we're not going to talk about multiple regression in this class, so let's actually just skip over that part. Non-parametric stats are distribution-free statistics. So we talked about parametric statistics, right, where you've got a Ttest, you've got an ANOVA, and you've got a correlation. Here, we've got non-parametric stats. So, and these deal with data at the nominal or the ordinal level. Right, so for non-parametric, think not real numbers. So remember, the nominal data is kind of just yes or no, right? Are the clients fluent at the end, or do they still stutter? Do they still have an articulation disorder, or are they within normal limits, right? So we don't really have data, we just kind of have yes or no. So these are going to be really conservative tests, meaning that, the tests, you're using, when you use these tests, it's assumed that you're using nominal or ordinal data, so you better have a really large difference, or it's going to say, no, there's no difference between groups here. So they're really conservative in saying, whether or not, yes, there is a difference or not. So here the data don't have to be normally distributed, right? Because if it's, we got 45 people came out being typically fluent adults, and 25 people were people who stuttered at the end, right? Well, there's no distribution there. It's just one number. So there doesn't have to be any kind of distribution, because we're not dealing with what we consider to be real numbers. So, and you don't really have to know the types of these. I'm not too concerned about that. The one sample Chisquare test evaluates whether the proportions of individuals who fall into categories of a variable are equal to hypothesized values. All right. So it compares expected values, if the null were true, with observed values. So let's say we wanted to go throughout campus and look at gender of people in majors, right? And we divide people up into male gender, female gender, and then we can add as many genders as we want to on top of that too. So maybe we could have 4 or 5 categories of gender there, and we could see, who's, what we could get then. We could get the gender of the entire university. So maybe we've got like 50% female, people who identify as female. Maybe we've got 46% who identify as male, and then we've got 4% of people who identify either as non-binary or something else. So, and then we take that 50%, 46%, 4%, and we look across majors, right? And then we see, so are we getting the expected value? Is that true across majors, right? So if we looked at communication disorders at nursing, right, we have much higher percentage of females than what we would expect based on the whole campus. If we were to look at engineering, at mathematics, right, we probably have a significantly more males than would be expected. So it compares the expected values of the whole university versus, and we can compare that to what we're actually seeing with observed values within our majors. All right, if that makes sense. Now we also have a MannWhitney U Test, and this is the alternative to a Ttest. We're going to use this for 2 independent groups, and it evaluates whether the medians of a variable differ significantly between the 2 groups. So we're not looking at means, we're looking at the medians. What are the middle scores? And we're looking at ranked data. So here you can't use it with nominal data. You've got to have at least ordinal data here. So it ranks the data. So here's a study that looked at differences between 2 independent samples. So it doesn't, we're not going to get the mean of the actual scores. We're going to rank the scores lowest to highest, and then we're going to look at the median of those ranks to see if those are equal or those are different. All right, so that ends our 3rd segment here in our lecture. Have a great day, everybody.